Friday we started with an example, right? That leads to a finite escape time. Which was that example? X square is equal to x dot equals to minus x square probably. This now. Before that, at the same time, could you please help me to list the particular properties exhibited by nonlinear systems but not linear? So far, what we have studied, that means properties which we see in case of nonlinear systems, but which is not possible or not next to impossible for linear systems. One by one, that is whatever we have learned so far.
Limit cycles of multiple equilibrium.
Limit cycle we haven't yet tested here. Multiple equilibrium points, right? Or rather, we should say multiple isolated equilibrium points. Why I emphasized on this word isolated? Anybody? Any answer?
No, there are no intersection between the region of attraction.
There will be no equilibrium point in their neighborhood of that actual
Good. Like, or what you wanted to mean, that is also close to that, although the sentence or the concept which you said that is not technically correct, but the idea what you wanted to give, that was correct. That is now what Kashyap said, that is multiple isolated equilibrium points means suppose this is there, this is there, this is there, okay. Then always it will be possible for us to find the separate region of attraction. Because otherwise, like if 2 is too close, suppose if it is something like that, then it will behave like only one equilibrium point. That is the problem. So this is a qualitative explanation, but and what is the exact information? Suppose you have a linear system, 1 by s into s plus 1, or even suppose 1 by s square. They will give rise to a continuum of equilibrium points. That is many equilibrium points in one region, and there we cannot distinguish them by drawing separate region of attraction. Like in this case, what I wanted to mean, suppose this is the region of attraction, 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 right? So separately we can see the existence of this equilibrium point. That's why we call them isolated equilibrium points. But if it happens, just a second, if it happens like that, that is in one region you have many of them for which it is not possible to draw this region of attraction separately, or we cannot find an epsilon neighborhood across this around these individual equilibrium points in that cluster, then we cannot call them as isolated equilibrium points. So for linear system already we have that continuum equilibrium points. it is already a phenomena which exists for LTI systems. So that's why in this point, if you miss this isolated keyword, then it may lead to a confusion. Yes, now that's what you are asking.
Abstract doubt in a way.
Huh.
My question is, if there are two equilibrium points, isolated equilibrium points, will the region of attraction of both the equilibrium coincide? Will there be a intersection of two ROAs?
There will be a boundary. The moment we say isolated equilibrium points, that means by default we are able to separate their region of attraction.
But sir, if my operating point or where my system is in between the two ROAs, then in that case how the system will behave?
Then it depends upon, suppose it is on the boundary line. Okay, suppose it is something like that. This is suppose the separatrix. Okay, this is the individual region of attraction. This is the separatrix, and what you are seeing, that is here, the point is there. Now the case is that should it come this side or should it come that side? Then it will depend upon, that is how much is the perturbation and the direction.
No, if there is no perturbation, like for example, we start with a system if there is no perturbation, and my initial state of the system is in between the two ROAs. That can be a possibility, right? So in that case, what is
We will exactly analyze this one. That is when after learning this thing. At this moment, I'm not able to exactly illustrate this point because the phase plane analysis is not yet done. So this is like one of the brilliant example. That is now itself, if you open chapter 2 from Khalil's book, you will see that is they have explained the case of the equilibrium points for simple pendulum problem, where the origin is a stable focus and then the plus minus pi comma 0, those equilibrium points are their nature is saddle point. So in that way I need to draw that phase plane. Then this point I'll be able to clearly explain. So for the time being I am skipping this one, but the moment we are equipped with the phase plane technique, then I'll be able to explain this properly. Okay. But at the same time, just a takeaway message is that isolated equilibrium points means where for each of those equilibrium point we can draw an epsilon neighborhood ball. This is called, I already introduced, epsilon neighborhood ball. Okay, that means with respect to this point, that is you can draw the ball, means that is in 2D it's a circle, in 3D it's a sphere. The concept is like that. It can be easily extended to n-dimensional system. So it is because I am drawing on a 2D plane, so that's why I am calling it as a ball. And for the same concept, even for n-dimensional system also we call it as a ball. Okay. So if I call that is epsilon radius ball, means that is how would you define this ball? This is for all x belong to Rn, so that in this way, that is mathematically we can define a ball of epsilon radius. In book you can find that is this may be r, this may be delta, depending upon the situation. So then that is it will also be r or it can also be delta. Okay. So this ball means it is of all the vectors such that the norm of those vectors is within epsilon. Okay. So now that is as I introduced the concept of ball. Later we will learn it in more detail. So one can be open ball, another one can be closed ball. An open ball means where this x, they will be strictly inside this periphery. That means they cannot lie on the border point. So this is the definition presently what I have seen, what I have written. This is for closed. Sorry, this is for open. That means the boundary points are not included. If it is closed, then it has to be lesser than equals to. Okay, that means then the boundary points are also included. So this means whatever x you can think about, its norm is less than epsilon. If it is 2D case, suppose if you draw it like this, that is x1 and x2, whatever, then all all these points, each one of them will have a coordinate x1 and x2. Then the meaning of this means is that root over x1 square plus x. Of course, you have to take the absolute value. So absolute value of x1 square plus absolute value of x2 square whole root under. This is the 2 norm, right? So that must be less than epsilon. That is the meaning. So maybe if you are not familiar with this notation, that is called norm. Okay, and at this moment we are using vector 2 norm. We have to learn little bit about norm, but not in this class. In sequence we will be learning everything.
Sir,
Yes.
this epsilon, what is the expression of this epsilon? Like
That
how
is, it is a number. It is depending upon that is what will be, that is how big is the region of attraction.
How do we decide that, sir?
That is a separate analysis. Depending on a system, that is how we can find the region of attraction.
Yes.
That is completely a separate analysis. At this moment, I am introducing all the notations and the terminologies.
What I mean, sir, like this making of epsilon neighborhood ball, is it in our hands or is it based on the system dynamics or specifically?
Of course, the system properties. That is whether, why, in which connection it has come. That is the moment you say isolated equilibrium points. That means it is guaranteed that for each of those equilibrium points, you can draw the epsilon neighborhood balls. Now, it can happen that is, suppose this is epsilon 1, this is epsilon 2, this is epsilon 3, and they are different. It is not guaranteed that is all of them will have the same. And also one more thing, that is by the term region of attraction, although it is a formal concept to draw a ball kind of region, but it can be a strip as well. That is, it can be like a strip as well. In case of simple pendulum, if you have seen that diagram which is drawn in Khalil's book, it's a strip, not perfectly a ball. So region of attraction, that is what will be, that is how big the attraction region will be, or what will be the shape. That is not in our hand. That completely depends upon the system dynamics. Here, that is, we are defining the terminologies. So that's why, that is, I am taking the help of the predefined, or which is the easier kind of notions, or which is very commonly we use this kind of shape or this kind of definition. That's why. But as you asked, that is the what will be, that is how you can find that region of attraction. That is a separate technique. While learning the Lyapunov, we will learn that one as well. But if you ask me, that is how big it will be, or like is there any guarantee that is it will be above certain thing. That is, suppose if someone says that is epsilon, it is 1 centimeter. Then if you say that is, can we make it 2 centimeter? No, it is not possible, because this is not in our hand. This is completely a property of that nonlinear system. Okay.
Sir, one more thing, mathematically speaking, if two isolated points are very very close, say we have this very small distance delta h.
When you are saying close, even there also we can then, epsilon is in our hand, so that's why we can always separate them out. Say for example, what you wanted to mean, that is if you have two isolated equilibrium points, suppose this is 1 and 2, there this distance is really very less. Just say for example 1 centimeter. There also we can think about individually. Epsilon 1 is epsilon by 2, where it is we can simply take 0.5 centimeter of radius. Similarly epsilon 2, that is also 0.5 centimeter radius. In that way we can think about. Even suppose it is not even 1 centimeter, it is 0.01 centimeter. 0.01 centimeter. That too we can divide by 2. So similar to the concept of infinity, this takes small. How small? Then whatever may be small, as long as it is not exactly equals to 0, we can always find an epsilon neighborhood. That is the concept. Like in case of limit, that is we try to approach towards 0, but it is not exactly 0. Here also the same thing. Is it now clear for all of you? That is, don't worry, that is at this moment everything I am trying to explain in language, because we are still not equipped with this explain technique. So that's why there is some doubts are still there. But don't worry, the moment we learn this explain analysis technique, so then one by one all this will be perfectly clear. Okay. So it is like all the discussion is regarded, is concerned with the point that if you mention the keyword isolated, then it may lead to a different thing. As I said, in case of LTI system, we can already have a cluster of equilibrium points where you cannot separate them by epsilon radius ball. So that is the case of continuum equilibrium points. Okay, so since that is already there in the case of some of the LTI points, so that's why this isolated keyword, that is highly important, because otherwise, suppose this is not there, you are writing only multiple equilibrium points, immediately it lead to a confusion that is, are multiple to LTI case में भी हो सकता है. Are you getting my point? Right. Then secondly, that is what else we know about the, as of now, that is we will be solving that example, but before that I am listing the peculiar properties exhibited by nonlinear system which are not possible or next to impossible for LTI. What else we have seen so far?
Sensitive dependency on initial conditions.
Right, they're very good condition. Dependence on initial condition. What else? Last day we were discussing about the non-linear oscillation, right, which will lead to limit cycles. Although that point is not completely clear to us, because last day I introduced that in a qualitative manner, but still you have understood that this non-linear oscillation is somewhat different from linear oscillation, right? Linear oscillation means that if you have a system 1 by a square plus 1, that will lead to a perfect sinusoidal oscillation. In case of non-linear system also, that is, we can have that kind of oscillation, but the cause or the nature, those are completely different. Okay, so as of now I am writing non-linear oscillation. In bracket I am mentioning limit cycle. Number 4, with respect to that example, finite escape time, which is not possible in case of LTI system, right? Remaining points we haven't yet introduced, but I just want to make a list so that they stay in your mind, and later one by one we will take up. Yes?
Different behavior of system based on the input.
Like a small change in input can cause a very high change in output.
Dependence on
Somewhat, that is, you can think about kind of a finite escape time.
What is escape time?
Escape time means, that is, last day we were discussing, that is, if you see the solution, it's subjected to this particular initial condition, xt will be 1 by t minus 1. Now you think about the trajectory. It starts from t equals to 0, then its time is increasing, suppose 0.1, 0.2, 0.3, and then it is starting from minus 1, so it was like growing, right? If it starts from, that is, t equals to 0, then that is x of 0 equals to minus 1. Then at t equals to 0.1, x of 0.1, what will be? Is this 1 by minus 1 by 0.9, right? Then suppose at t equals to 0.2, x of 0.2, that will be minus 0.8. Similarly, after that it will be minus 1 by 0.7, right? So in that way, you can see that is this amplitude, is it increasing? Yes, it is increasing. Starting from minus 1, it is increasing, but it is continuous, right? There is no discontinuity before attending t equals to 1 point. But the moment you have t equals to 1, then x of 1, that will be 1 divided by 1 minus 0, so it goes to infinity. So suddenly, within a finite range, it can go to infinity. That is called escape time. This particular phenomena or this kind of phenomena is not at all possible in case of LTI system. That is, everything was going fine it was like it is a continuous function, it was increasing or decreasing gradually like a continuous function, but all of a sudden it breaks or it explodes. This kind of thing is impossible in case of LTI system. So this is called finite escape time phenomenon. Then what else? Bifurcation and chaos. Yes, although that is we don't know them, but we will know them a bit later. Bifurcation and chaos. At this moment, we don't have any idea about them, but they have some different kinds of phenomena. That is also exhibits some peculiar phenomena which is not there for linear systems. Anything else? What is the main difference or which we all studied while learning the LTI system?
They have different solutions.
Superposition doesn't apply.
That is by definition, but
Sir, we can go solve them in frequency domain, and we have many analysis methods where we can get the solutions, but in case of non-linear.
but that is not a property, right? That is some techniques fails or some techniques succeed. That is not a property. These are some of the peculiar properties or behavior. Are you getting? That is another behavior is that for LTI system, that is if you excite a system with a particular sinusoidal wave. Say for example, if you excite a system, it is G, and suppose this is sine omega t. This is known to all of you. This is the input U. Then Yt, if it is LTI system, the frequency must be the same. So it would be somewhat, it is, suppose if it is like Um sin omega t, then it would be Ym sin omega t plus or minus phi. Of course, a phase difference will be there. So now, if it is LTI, then what is guaranteed? That is, it will be the same omega. But if it is non-linear, then of course that will not be maintained. There will be multiple frequency components, right?
Subharmonics, submultiples.
Multiple frequency components. Hassan, what you were thinking, that is the sub or supersynchronous frequencies, but that depend upon specific non-linear systems. So that I cannot comment in general. So that's why here I can write only multiple frequency components.
So, stability.
Huh?
When we talk about stability here, stability exists only in a finite region. Unlike
That's what I mentioned, the dependence on initial condition. That point that is will come under this point, okay? I will explain that. Multiple frequency components. That is the main distinction between the linear and non-linear system, right? That is when, if you remember, that is when we studied the stability properties of LTI system, then it was one of the very common explanation. That is, if you excite an LTI system with a fundamental sinusoidal frequency, whatever may be the omega, if it is only one component, then the output is also expected to have the same frequency component. The phase can be there, the amplitude can be different, but the frequency cannot be different. That is one of the signature properties of linear system, right? But in non-linear, of course, there will be then a mixer, like mix-up of all the frequency components. Okay. Now, that is related to that, there can be a property of subsynchronous or resonance. Subharmonic resonance. Again, like the same thing, at this moment we don't have any knowledge about that point, but we will learn, okay? Subharmonic resonance. Any other point that comes to your mind? If you have any doubt, please feel free to ask. at this moment I'm not at one by one we will learn. Okay, ये जो subharmonic resonance ये अभी तक हम लोग को पता नहीं है, इसीलिए मैं एक्स्ट्रा किया. जैसे ये पॉइंट भी bifurcation और chaos ये अभी तक हम लोगों को पता नहीं है. But I'm listing the properties, that is one by one we will learn them. Okay.
This basic property cannot be represented in terms of transfer function or state.
That is already, but that is the technique that ceases, right? Because the nonlinear system, by that term nonlinear, it doesn't satisfy the principle of superposition and homogeneity. And the transfer function we can like find for the LTI systems, right? So that is the reason, that is why we cannot explain. But that you can say, that's what I said. I think it is not a property. Their transfer function is a technique of representing a system, right? So that is frozen, or that is not possible in case of nonlinear system because of the nonlinear property. So separately, I cannot list it as a property, right? So that's what I didn't. But if you think about the differences, of course that is a subtle difference, but I cannot say that it's a property. You can talk about that it's a result, it's the reason why transfer function approach ceases in case of nonlinear system, because it doesn't satisfy the linearity property, right? Are you getting that? Is Fayaz wanted to say that is this nonlinear system, we cannot apply the transfer function technique in case of nonlinear system. Why didn't I list that as one of the points here? But what I wanted to mean, that is not a property of the nonlinear system. Transfer function technique is an approach which is not valid for nonlinear system, that comes because of the property of being nonlinear. So it doesn't satisfy the linearity property, that's why we cannot apply the transfer function technique, right? And also that is the transfer function, if you ask me that is what is the core reason. In case of a nonlinear system, it contains or it gives rise to multiple frequency components. Whenever that is we talk about the transfer function representation, so that is it takes one specific frequency or a few particular frequencies, all zero, they are nothing but the frequencies, right? But nonlinear system, they will give rise to a series of frequency components. So that's why how would you express it by a transfer function? That is qualitatively you can explain. Okay? And then that is some of you that is asked the dependence upon initial conditions. So like I think that is we had some confusions regarding the equilibrium point and their stability. So I try to take up that point now. Before that is can we solve this problem? Fast, please don't talk. Can we solve this problem now? Because that's what we have been waiting for. So, dx by x square equals to minus dt, right? Then you integrate both sides. Dx by x square equals to minus integration dt. Now, of course, it is an indefinite integral, so we have to take the help of a c. And if it is so, then after that, what will happen? What will happen? It is isn't it? Minus t plus c, right? So minus 1 by x equals to minus t plus c. Is it fine up to this much? Now to find out the c, we have to use the initial condition, right? So c is how much? Now you have to find the x0 equals to minus 1. x0 means x at t equals to 0. So that leads to, it is minus 1 by minus of 1 equals to 0 plus c. That gives c equals to plus 1. Then after that is if I reconstruct. So 1 by minus x equals to minus t plus 1, right? Let's see, that is how it goes. So now x equals to, what happens? That is minus of, 1 by 1 minus t. So it is 1 by t minus 1. It's an easy integral, right? Now you see, that is, if the initial condition not only for minus 1, I think that is as long as it is minus, this the same kind of like the pattern will come, right? But if it is positive, suppose if it is instead of plus 1, then I guess it will become 1 by t plus 1, right? So that is now that if you consider that is for all negative initial conditions, I believe the finite escape time behavior will be there. But if it is positive initial conditions, then we don't have any problem, right? So, is it fine, this one? Then that is like, I wanted to like check up this point further, there is dependence upon initial condition. In between, like, do you come across any other point which can be different properties or which can be a property for nonlinear system?
Sir, I read
Huh. Any other property which we haven't yet discussed? Vishwana?
So I have a question regarding initial part.
Huh.
So here x of naught is x naught equals to minus 2. So that's mean it's a static initial point. So can it be dynamic?
How a initial point can be dynamic? In case of a differential equation, initial condition should always be a constant point from where it will start. It cannot be dynamic. It can be different points. Say for example, in case of minus 1, it can be minus 2, minus 3, or then plus 1, plus 2. But initial condition has to be mentioned, and that is a constant quantity. It cannot be varied. Because why it cannot be varied? Because you see the t coordinate, x of 0. That means x at t equals to 0. That's why initial condition has to be a constant. I think that is your query lies somewhere else. Maybe you couldn't express that well. You think once more. What was your original doubt?
Yes, sir, I will.
Okay. You wanted to say something?
Sir, I read in the book that frequency of oscillation depends upon amplitude of motion.
Huh.
I could not understand
That is here, like that day I talked about. Van der Waal equation, that is how I represent it.
X double dot.
X
In y double dot plus c y square
Huh.
minus 1 y dot plus k y is equal
in
to
y double dot plus c
Y square
into x
minus
is
one.
y square minus 1, right?
Why not?
Y
y dot
square minus 1 y dot
plus ky is equal to
y equals to u or f, whatever. Then that is, we can also represent it in the state space format, right? In the state space format, how does it look like? Of course, that is if you consider x1 to be y and x2 to be y dot, then x1 dot equals to x2 and then x2 dot
minus k by n x1.
exactly. minus k by m x1
Minus
then
G by M.
minus c by m, right? Isn't it? Minus c by m then x1 square minus 1 into x2. Plus 1 by m, if you write a for whatever. This is the famous van der Waals equation. This is one of the signatures nonlinear system. Why? Because like before that, like before not attending nonlinear control classes, we all learned spring mass damper system, and every time that is we used all the linear components. That is my double dot plus dy dot plus ky equals to f, right?
So sir, is this the same as Duffing equation?
Duffing means you will have one more component. That is the most generic form where both the spring and dashpot they can be nonlinear. So in case of if it is LTI, my double dot plus dy dot plus ky equals to f. Okay, so that is the linear spring mass damper system. Linear spring mass damper system. So if you compare this one with this one, then what did you see? The mass block remains the same. There is no nonlinearity regarding that. Spring also at this moment remains the same, ky. Although spring can also be nonlinear, but at least in this equation, spring remains the same, linear. But you see there is a major change in the damping action. Now, my damping action is no longer proportional to only the velocity. Now, it is a something very peculiar type of relationship. C is of course a constant, like here I use D. So, if you have a problem here also, that is I can write C so that you can compare it easily. But now you see it depends upon, that is here the damping depends upon also the displacement. And that too, it is not a linear variation, it is a non-linear variation, right? C into y square minus 1. Now, that is all of you know, the positive damping means it will help in the stability. Negative damping means rather the oscillation will grow. Now you think about the situation, if your displacement at the beginning of the experiment, when the displacement is really very less, if it is less than 1, then what will happen? It will have a negative damping, right? Negative damping means the oscillations will grow. But if your y is more than 1, of course y square will be greater than 1, then the damping will be positive, so the amplitude will reduce. But now what happens, say for example, if you start with an initial condition, that is suppose your x0, initially suppose if it is more than 1, say for example it is 2, 0. Okay, with that it is starting. So then what will happen? That is, it's a positive displacement. The first coordinate is for y displacement, the second one is 0, the velocity. Like suppose you have just displaced the mass block by your hand to create a non-zero initial condition, and then you release to see that is how it will vibrate. Okay, you have a suppose spring mass damper system. Physically you have a mass, then in one side you have a spring connected to that, the other side you have a dashpot, and then they are connected to the wall. Okay, and in that way, that is, if you have to carry out an experiment, you have to apply some force driving factor. So I repeatedly, I said many times, that is driving factor can be of two types. One is you specifically apply a force, or else you create a non-zero initial condition. In case of the spring mass damper system, if I ask you to create a non-zero initial condition, what will you do? Suppose this is the mass block, spring and damper, everything is there. Then you have to stretch it like that. Not straight, you have to physically, that is, you have to change the initial position, and the moment you leave it, then immediately the oscillation will start. That is called, that is, we are creating a non-zero initial condition. Okay, but providing a force means then you have to take a probe and function generator or any kind of external means, we will continuously give a force. Okay, so force can be a driving factor. Again, non-zero initial condition, that can also be a driving factor. Okay. So say for example, we have created this non-zero initial condition by our hand. So there is no external force, but a non-zero initial condition is acting as a driving factor. Then what happens? Damping would be positive. Damping positive means that is the amplitude. At this moment, don't think about any oscillation. Just you think that is here the what will be the oscillation graph. Okay. So if this is y-axis, if this is t-axis, so suppose this is the one coordinate 2. So this is the point from where it will start. Okay. So gradually it will start and then it will go down because now the damping is positive. That is how far it goes down, that we don't know. That is, had it been an LTI system, then if simply it would have been a underdamped, a second order underdamped. That is, we are like very familiarized with that. But here we cannot say that is it will be something the oscillation will decay down. That is not the phenomenon. Here what will happen, why the peculiarity arises, you see, yt from 2, suppose it is now decreasing, 1.5, maybe 1.8, 1.5, and after that 1.3, in that way 1.2, then 1.1, then the moment it becomes 1, what will happen? It becomes an undamped system. So that is, after coming here, what will happen? If I use a different color chalk. Okay, now so this is one particular case. Next, another one, suppose you start the initial condition from somewhere else. x0, suppose this is our first demonstration, so I am writing x01. Here if I write x02, let's start with plus 0.1. Then what will happen? You see that is 0.1 square minus 1. Of course, it is now the damping is negative. So negative damping means the amplitude of the oscillation will increase, right? So suppose that is now what about the situation for x1? x1 means y of t. So from 0.1, suppose it goes to 0.2, then 0.3, 0.4. The moment it reaches 1, then the damping, from negative damping, it becomes undamped. So here at the same time, suppose if it starts from here, it grows. The moment it reaches 1, after that, it will exhibit the same oscillation. At this moment, we are just learning the phenomena. Later, we will learn it after when we will discuss the limit cycle. Then, that is, we will learn the maths against it. At this moment, what we have learned, suppose this point is x01, this point is x02. Here, that is what MITI asks. That is, in case of nonlinear oscillation, the amplitude, it doesn't depend upon the initial condition, which is not the case of LTI system. In that regard, I drew this graph. That is, whatever may be the initial condition, finally, for as long as these parameters remain constant, it has a particular amplitude of oscillation. That is called nonlinear oscillation or limit cycle phenomena. Are you getting? Once again, that is, suppose it starts from 2, 0, and the second case it starts from 0.1, 0. Okay, so in one case it starts with positive damping, in the other case it starts with negative damping. Last day, that is, when I was explaining, I missed only one point, that is, starting like whether at the beginning it is a positive damping or negative damping, but the moment y becomes equal to 1, that means the system becomes undamped, after that it will remain in that situation. I missed only that point. Are you getting? That is this here why the oscillation comes. Any kind of oscillatory system means damping equals to 0. That is when you write, that is one by a square plus 1. We call it as a linear oscillatory system. Poles plus minus J1. If you express it in the form of 1 by a square plus 2 zeta omega ms plus omega m square, then you compare this a square plus 1 with this. Now that is immediately you can write the damping factor zeta equals to 0. That is the case of undamped system. Okay, here also you compare with that. The moment y becomes 1, then the damping becomes 0. That means it becomes undamped. So if it becomes undamped, then we cannot do anything. And that is the reason why the oscillation starts. That is called nonlinear oscillation.
Sir, that y is becoming 0 at one particular instant. Right?
But once it becomes that is undamped, if there is like in the ideal case, if there is no other factor which is changing the damping, then it will remain undamped.
So due to the inertia of the block, it will never be at y is equal to 1. The moment it becomes y is equal to 1, then it will change. It will continue.
No, but it is happening within the inertia only, because in the inertia, in the m term, there is no change. Here, when your damping is a nonlinear term, so where we can see that is it is y square minus 1. In the ideal condition, even in practice also, if there is no other factor which can change the damping term, it will remain undamped, because you see mathematically we don't have a second term which can provide a negative or a positive damping. So the moment it becomes that is 0, undamped, so it starts the oscillation, then there is no other factor which can increase or decrease the damping. That is the reason.
But still the damper is connected to my physical system.
So here it is coming from the physical system only. So you see that is if you simulate this, that is at this moment I cannot simulate, but I insist all of you that is you use the Simulink to like simulate this. Then that is it will be a brilliant demonstration, because like this we are learning this for the first time. So of course all of you will have the doubt that अरे ये कैसे हो सकता है, linear system में तो कभी भी ऐसा नहीं हो सकता है. तो इसलिए it is highly required that is you simulate this. Okay, the data you can either take from Khalil's book or even in Slotin books also it is there. You just create two different initial conditions and then you see that is how the amplitude of like how the oscillation goes on. Okay, so what is the takeaway point? That is whatever may be the initial condition, that is finally for a particular system, that means for a particular given set of parameter values, the amplitude of the oscillation will remain the same, which is not the case of LTI system. Why? Can anybody tell me that is why that is not the case?
Different input will result in different amplitudes.
For any kind of LTI system,
Yes, I
your
agree.
YT that will be C into e to the power 80 into x0, right? I'm talking about the free response, because it is about creating non-zero initial condition, means it is still a free response, not a forced response. So YT would be C e to the power 80 x0. Now you see C is for a particular system, A and C those are fixed, but x0 it varies, right? So if it is a noun, that is if the A is of this kind, suppose it's a like if A is here, sinusoidal system is 0, 1 and then 1, 0, right? If the situation is like that, then it will be giving you a sinusoidal oscillation, that is sine omega t plus theta something, but x0 will still be there. So that's why the amplitude of oscillation, it still remains, it still depends upon the initial condition. But here the phenomena is quite different. So that's why although the phenomena is oscillation, but there is a huge difference between linear oscillation and non-linear oscillation. Only ultimately the graph that we see, that is a sinusoidal graph, both in these cases, but the reason, like the cause and the nature, both of them are completely different. So that's why actually, although we call it a nonlinear oscillation, but actually the phenomena is limit cycle. Is it now clear to you? So from this graph we could see that is whatever may be the initial condition for a particular system, the amplitude of oscillation will remain the same. At this moment, still we may not be 100% convinced, because I couldn't take up the point mathematically. Everything will be we will see the mathematical expression, that is why it remains constant. But at this moment, I am just disseminating the information so that they all stay in your memory. That is okay. In case of nonlinear, we have this kind of peculiar phenomena. But please wait till that class when we start the limit cycle formally. But again, that is for linear system, what will happen? That is, as you can see, that is, if you write that there is some amplitude A and then sine omega t plus or minus phi, whatever, then this amplitude A, that will contain this initial condition x0. So that's why for linear oscillation means its amplitude will definitely depend upon the initial condition, but which is not the case of a nonlinear oscillation. Okay? So you can take a note, although the oscillation keyword remains the same, but the cause and the behavior of linear and nonlinear oscillation are completely different. Hassan, at this moment, that is, I couldn't make you fully convinced, but please wait until we start the limit cycle.
The only thing is that just because the value of y is continuously changing, because that's
but why does the value of y change? You think about the
because
cause.
of the positive and negative dimensions.
If it is a linear time invariant system, then if your zeta, if it is in between 0 to 1 under them system, then that is why when we follow that in an exponential envelope, it is going like that. What is the reason? Behind the damping, because the damping force is there.
Zeta.
But if zeta is 0, if it undamped, then what will happen? There also it's a dynamic system. Then why does that oscillation continue? Same reason. The doubt that you had, that is, if it is a dynamic system, if there is inertia, then the oscillation should not continue. Then in case of LTI system also, the sustained oscillation shouldn't have continued, but it continues, right? Because it comes from the solution, that is, you write down the solution of the differential equation, from that it would be visible. Damping is 0 means definitely at that particular situation, there is no restraining force on the system. That's why that is damping close. Have you understood his query? That is, Sasan was saying, you have a spring mass damper system. Okay. Now that is, if all the components have some inertia, that means all of them will exert restraining forces. So then how could it be possible that is at one particular moment the damping becomes 0 and after that the oscillation will continue? So can anyone explain this point?
So the equation itself changes after y equal to 1.
Sir, it is due to the fact that this particular system is demonstrating a cyclic behavior of positive and negative damping.
In linear system also, the cyclic behavior. See, that is I think that is the physically, that is, you might be thinking about the physical reason. The inertia, that mass block, it gives the inertial force, that is, which is m into alpha. Spring, it gives the inertial force k into y. Dashpot, it gives I should not say inertial, also of them that applies the restraining force, that is d into v. Now what happens, suppose the dashpot is not there, right? Only the inertial force would be there and the spring force would be there. And if the dashpot is not there, there is no energy dissipating element, then what will happen? The oscillation, that is, will keep on growing. But it doesn't grow with respect to time. Why? Because at least the spring is there. That means one kind of damping, although spring is not a damper, but still one restraining force is there. Because you just think about, that is, if it is only mass block, then what will be the transfer function? 1 by m into a square, versus if you have only this mass and spring, then what will be the transfer function? 1 by m square plus k, and now it is versus 1 by m square plus cs plus k. Now you compare between these three. The undamped means somehow that c has become 0.
The same thing that happens with the tank circuit, so it's the same thing, right? The exchange of energy keeps on happening.
So it is from underdamped to going to undamped means the C is becoming 0. Now C is becoming 0, that means the specifically damping term has become 0, but there is still some restraining force because spring is there. So that's why at least it is a sustained oscillation without having a growing amplitude. If the spring is not also there, if it's simply 1 by s square, then what will happen? That is, then the response will be like that of a ramp, right? So in one case, that is, it is a decaying oscillation. Another case, it's a sustained oscillation. Sustained oscillation means the amplitude of oscillation will remain the constant, but at least not a growing oscillation. But if it is 1 by s square, then what will happen? It will follow a ramp, or maybe if the input is there, it will be parabolic. So now you compare that situation in case of nonlinear system as well. Suppose this c into y square minus 1, this whole thing, it acts as zeta, or this is the whole damping term zeta. But now zeta is not a constant. Zeta depends upon the one of the state, here displacement. So if now zeta becomes 0 and there is no other component which can make zeta positive, then what will happen? The system itself says that the oscillation will continue.
Sir, but that zeta is dependent on suppose y, and this y has made that zeta 0, but that y is continuously changing, no, sir?
No, at that point, that is, there is no other factor which will bring more damping. So if you, like at this moment you see why the doubt why the confusion arises, because we don't have a closed form solution. That is, if you can find out if you can solve this nonlinear differential equation, if you then write y, immediately it will be clear to you. That is what we are using physics, what we are trying to understand, that doesn't defy the mathematics. What you wanted to mean, that is वो एक particular point पे वो 0 आया, damping 0 हो गया, उसके बाद वो तुरंत कुछ damping आना चाहिए. अगर y का equation अभी available होता हम लोगों के पास, immediately that will be clear.
Sir, so then in this case the right hand side should have been 0. It should have been an unexcited state.
That is here, that is when we test this kind of phenomena, then it is subjected to non-zero initial condition. Then of course, that is it would be the forcing function is 0 and the experiment is subjected to a non-zero initial condition. That means that's what I already mentioned, that is x0 not equals to 0, a non-zero initial condition, that will be the driving factor. Okay. So, but when we will learn the limit cycle, then all that theoretically we will study this characterization or the behavior of nonlinear oscillation. Okay. At this moment, through this example, I wanted to give you the feeling, that is a basic understanding of what is a nonlinear oscillation is. Okay. And also, I believe that is you have understood that is while the linear oscillation, amplitude depends upon the initial condition, but in case of nonlinear, it doesn't depend upon the initial condition, right? So that is the main distinction between linear oscillation and nonlinear oscillation. Now that is coming back to one of the things, that is the stability of the equilibrium point. once again, that is, we will take the help of this pendulum system. That is, what was that? Can you tell me? Theta double dot plus G by L sin theta, right? G by L sin theta. So this is the pendulum, and if I write state variable, then suppose x1, that is theta, and x2, that is theta dot. Okay, then x1 dot equals to x2, and then x2 dot minus G by L sin x1 minus G by L x2 plus u, right? See why all these doubts are arising, because that is what that is maybe on the first day or the second day I explained. That is, stability of a linear system, it doesn't depend upon the input or also on the initial condition. Like that is, for the time being, if it is LTI, you have a transfer function two main stability notion. One is Bibo, another one is asymptotic, right? Bibo stability, another one is asymptotic stability. Here we should call it in the sense of Lyapunov. Bibo stability means whatever bounded input you apply, the output will be bounded, right? That is the concept of Bibo stability. And then asymptotic stability means there is we are talking about free response. Bibo means we are talking about forced response, right? So in bracket, if I should write x0 equals to 0, but u not equals to 0. In bracket, I am mentioning like all those extra information so that later when you revise, it like helps you to remember all the points. Okay. Bibo stability means specifically the initial condition must be 0. That means there should not be any free response we are talking about, or we are like checking the force response only. Okay. And now asymptotic stability, especially when it is Lyapunov, then your forcing function must be identically 0. That means here we discuss or we test only the free response. So x0 not equals to 0. Right? So then what is asymptotic stability? Xt, that is e to the power at x0. Now here what is the concept of stability according to Lyapunov? That is starting from an initial condition x0, whether it remains bounded for all time, and if it is so, then whether it goes to 0 or not, right? So actually, let me write this. This is called, I will explain, don't worry, this is stability in the sense of Lyapunov, okay?
But sir, earlier we defined energy like function and then
Same thing, that is, then here I am only defining the stability, then if you ask that is how we can reach, that is how we can show it, then we have to take the help of energy function. Here, one is the definition of stability in the sense of Lyapunov, another one is Lyapunov stability theorem. I hope you got confused between that two. That is a very essential point. Although it sounds funny, that is मतलब वो एक ही कुछ keywords को मैं आगे बोल रहा हूँ, पीछे बोल रहा हूँ, but दोनों के बीच में काफी फर्क है. I am going to write. The stability here, boundedness of states. Here you must write stability in the sense of Lyapunov. Can you somehow arrange for 2 more boards? Like always I face the same issue, that is I do not have enough space. Nitisha, can you do something? MIT. अरे तो कॉटन कॉलेज में भी तो है, हम लोग को इधर नहीं है, कॉटन कॉलेज में भी है ना. अंजन सर बोला था मेरे को. See, always it happens that is when I start discussing something, but in between the related things come, and then I deviate in another direction. But you please keep track. See, at this moment, that is, if I have to explain the stability of nonlinear system, then immediately these concepts will come, especially the stability in the sense of Lyapunov. Now, if I don't explain them, definitely you will have some void in understanding the stability of nonlinear system, and it happens everywhere. So that's why you might have seen that is like when my class extends along and then I keep on saying so many things, but of all of them are relevant. Your job is to note everything in a sequence. Later when you will see, that is you can relate, that is why I brought those extra things. Right? And that is also the reason why BTech students don't at all like me, because they always want to get the class finished within the 55 minutes, and they always want to have a very less amount of syllabus, and I keep on explaining so many things which may be helpful for PhD students and MTech students, but for BTech people they don't like it, and every time they write a comment that is the instructor takes extra class. This time 2 of them wrote the instructor is clearly biased towards MTech and PhD students. So that is the problem. But anyway, that is, I don't mind. Coming to that, one is stability in the sense of Lyapunov. Like last time also I said, within the stability there are 2 classes. One is just stable, that means the states are bounded, and then one more favorable condition which is asymptotic stability, right? So stability here, I wrote boundedness of the state. Okay, this is the first requirement. And then one special case is that if it implies, or rather we don't know when it will imply, that we'll have to see. Norm of xt goes to 0 as t tends to infinity. This is equivalent to saying the whole xt tends to 0 as t tends to infinity. Okay, this is equivalent to saying this is norm. Norm goes to 0 means individual state component should also go to 0. Okay, so I am writing equivalent to xt goes to 0 as t tends to infinity. This concept, it is called the stability in the sense of Lyapunov. Now what does that mean? That is one of the main question. That is, here I wrote, that is, if x0 implies means if this happens then it will happen, right? Sorry, that is, if it is true then it will happen. So here you see, that is, I tried to put a bound on the initial condition, and if it is so, then after that we will have some good results, right? That we'll have to understand. Suppose you have a system x dot equals to f of x, and then x0 is not equals to 0. Okay. Now what does that? This is the system. With respect to this system, I'm like trying to explain this condition. Okay. Suppose this is delta